Welcome to lesson 3 of week 6. In this lesson, we're going to learn about logic circuits. You're going to make a circuit by joining logic gates together and draw the truth table for the circuit. We're going to go through a couple of worked examples and then there are some exercises for you to do yourself. Logic circuits are made when we join logic gates together. That means that a wire or channel goes from one gate to the next. So the output of the first gate becomes the input of the next gate. In all the examples in this lesson, we'll use just the and not gates, but in later examples, we'll use the full range of gates. So here are the two gates. You've already learned these. The effect of the NOT gate is to reverse a signal, and the effect of the AND gate is to be off unless both of its inputs are on. We can join them together. We draw it like this, and physically, we would literally physically join them together with some kind of electrical conduction. So you can see that the output of the NOT gate becomes one of the inputs to the AND gate. A good way to talk about logic circuits is to label all the inputs and outputs. So that would be how we would typically draw a logic circuit made out of a NOT gate feeding into an AND gate. And it's easy, set out like that, it's easy to understand. Now we're going to make a truth table based on this circuit. And we look at the circuit, we label all the inputs and outputs of all the gates, and then we count how many letters we've got, and we make a truth table with a column for each letter. Let's look at what that would look like. So there are 4 inputs and outputs, A, B, C, and X. Conventionally, I tend to give all the inputs and outputs consecutive letters of the alphabet, except for the final one, which I give a letter which is at the other end of the alphabet. That's just how I typically do it. Now we've got to enter all the possible values for A and B. A and B are the inputs to the circuit, and the truth table must show all possible combinations of A and B. A and B are independent of each other. That means that if A is 0, B can be 0 or 1. So the 4 combinations are 0, 0, 0, 1, 1, 0 and 1, 1. You'll see immediately that those are the binary digits counting up from 0 to 3, 0, 1, 2, 3. So I always set them out like that, like binary counting, and that is what we conventionally do. And that makes sure that we don't miss anything out. The truth table would still work if we had them in a different order, but this is a way of setting it out in a methodical way to make sure we don't miss anything. Okay, so what is the formula for value C? Value C is the output of a NOT gate, and the input to the NOT gate is value A. So C is equivalent to NOT A. So let's write that in. There's A, and there's not A, because the NOT circuit reverses the truth value of the wire going in and produces the opposite. Now, what about value X? What's the formula for value X? Value X is C and B. X is the output of an AND gate, and the inputs to that gate are C and B. So X has the value C and B. Can you see what the values of X should be? I'm about to show you. So here's C and B, and X is only true if B and C are both true. So in the second row, and that is the only circumstances in which the circuit produces an output. So let's just recap what we just did to create a truth table from a circuit. This is a very simple circuit. Later on you'll be producing the same, using the same method with much harder circuits. So label all the inputs and outputs with letters. Draw a truth table with a column for every letter. Enter the input values. A good way to do that is to count up in binary from 0. Find the Boolean expression at the top of each column and then fill in the column with the values. So input and output of each gate, a column for each of those letters, binary counting. When we look for the Boolean expression at the top of a column, we should think, what is the gate that is the output of? Is it an AND gate, a NOT gate, or XOR? What is the operator, in other words? And what are the inputs to that gate? And then finally, now we know the Boolean expression, we can just work out the value of that output for each row of the table. Let's do another one. It's AND and NOT gates, but they're just wired together in a different order. So, step 1, label the inputs and outputs. Why don't you follow along with this in your book? So just scribble this down. It's just for yourself. Do it in your book and see if you can stay one step ahead of me. So see if you can label the inputs and outputs. If I'm not giving you enough time, pause the video. So that's what it would look like with all the inputs and outputs labelled. I've arbitrarily made the final output Z. Now draw an empty truth table. You could do several steps if you like, but these are the steps as I'm doing it. Label the inputs and outputs. Draw a truth table with a column for every letter. There we are. Can you remember what the next step is? It's to fill in the values of A and B, so do that now. There they are. Binary counting. And now next step is to work out the Boolean expression for each column and then to fill in the values for that column. So let's do that. What's the Boolean expression for C and what's the Boolean expression for Z? So C is A and B and Z is not C. So I'm going to fill in those values now. See if you can do that, staying one step ahead of me. So C will be only true when A and B are both true, and Z is obviously the opposite of C. So there we have it. This, incidentally, is the equivalent of a NAND gate, but as I say, that's not going to come up in the exam. So, we've been through a couple of examples, so I'm setting you the challenge of drawing the truth tables to match these circuits. So, pause the video now, and sketch those circuits in your book and draw the truth table to go with each one. I'm going to show you the answers in a few moments. Okay, so that was circuit 1 that I set you to do. And there's the answer to that. You'll see that these circuits are made entirely with AND gates and NOT gates. And if you haven't tried the second one, go back, scroll back, see what the circuit is. I'm about to show you the answer to that one. And here's the second example. Did you get it right? Hope so. If not, go back and check what I've been teaching. Okay, so in the next lesson, we'll look at the relationship between circuits and Boolean expressions. So remember your Boolean algebra expressions. We're going to be dealing with those in the next lesson. All right, bye for now.